Thank you very much. I'm Holly Cummins. I work for Red Hat. I'm part of the team that helps build Quarkus. And I like talking about Quarkus because I like talking about efficiency. But in fact, almost through my whole career, I've really been talking about efficiency and thinking about efficiency. I started my career looking at garbage collection in the JVM. And of course, with garbage collection, the one thing that you absolutely want to do with garbage collection is make it more efficient. Actually, there's two things that you want to do with garbage collection. The first is to make sure it doesn't lose your data. Once you've solved that problem, you want to make it more efficient. And then I switched focus, and I became a consultant. And so I was working with organizations, and I was trying to help organizations really take advantage of lean, trying to take advantage of extreme programming. And there, really what we're trying to do is we're trying to get that flow. We're trying to get that organizational efficiency. And of course now, as I mentioned, I work with Quarkus, which is wonderfully efficient. But I first realized that although I cared a lot about efficiency, it seems that our industry maybe didn't care as much about efficiency as I hoped. And in fact, our industry had a really bad efficiency problem. And I realized this when I heard a story from some colleagues. And this was many years ago. This was before the cloud, if you can imagine such a thing, if you can remember such a thing. And we had made some software that could provision a system in 10 minutes. Now, at the time, now this sort of seems like, well, what are you doing with the other 9 minutes and 59 seconds? But at the time, this was amazing. And so we sold it to some clients, and they came back to us and they said, well, this software doesn't work. It doesn't take us 10 minutes to provision something. It takes us 3 months to provision something. And we thought, that's odd. I wonder what bug that is. So we looked into it. And it turns out the problem wasn't a technical problem. The problem was that they had put an 84-step pre-approval process in front of the 10-minute provisioning. And when you look at it like that, you think, actually, it's amazing that they were managing to get things provisioned in 3 months rather than longer. And I mean, this is just terrible, and this should make you angry because there's so much waste in there. And there's all sorts of problems with waste. But now, one of the biggest problems with waste is that waste is killing the planet. We really need to care about waste if we care about ourselves. But what is waste? Well, as a species, we started thinking about waste about 300 years ago. And we started thinking about waste when we started thinking about efficiency. And we started thinking about efficiency when we really started to build machines, and when we were inventing steam power. And how many of you have studied physics? Yeah, I did as well. I firmly believe that physicists make some of the best software engineers. I do have a bias here because I studied physics. But for the rest of you, you'll have like a little bit of a physics education after the end of this talk, so then you can count yourself among that group as well. So in the 1700s, they were looking at steam engines. And they worked out that when you make a steam engine, the process is that energy comes in, and then energy goes out at the other side. This is technically correct, but it's not really informative enough, because what they actually cared about was the fact that two kinds of energy came out the other side. One was useful energy. That's the energy that makes the steam engine go forward. And the other energy is waste. And usually there's a lot more waste energy than useful energy. And so this was such a good idea that the management consultants, or whatever the 1800s equivalent of a management consultant was, took the same idea and they applied it to processes. So if you have a process, time and money goes in, and then hopefully value comes out the other end. And this is really all about people. And so the people get value, but then there's also waste that nobody benefits from. And we can extend this even further, and we can extend it to manufacturing. So if you have a manufacturing process, materials go in, those materials have some value, and then other materials come out that hopefully have more value, but there is waste. And then we extend this idea again to software. So if you have a computer system, you put time, electricity, hardware, programmers' tiers in on the one side, and then on the other side, you get answers out. But you also get waste. So you can see that we've got really good at generating all sorts of different kinds of waste with all of these processes, which is bad because waste is killing the planet. So e-waste is killing the planet. Every time we buy a computer, that computer then has an end of life at some point in the future, and it just ends up as e-waste. And every time you run a computer, there's a huge amount of energy waste that's created, both from heat, but also sometimes even just from the computation itself. Slow code is killing the planet. And this is everywhere. I heard a story recently that the LinkedIn research team had a new feature, and they were really excited about it, so they went off to do user studies, and they went to Nashik in India, which is about 100 miles away from Mumbai. It's a city, but it's not a large city. And so they sat down with the users to try this new feature, and the new users basically had a blank screen. And what was happening was that the connectivity was so poor, and the software was so bloated, because it was downloading half of the internet into the browser, that it just didn't work at all. And this is a huge problem for all of the modern web. We have so much bloat, we have so many layers of infrastructure, we have so many layers of framework, that it's fine if you've got a good network connection, and it's actually useless otherwise, which is the case for a big part of the world's population. And then we have another problem, which is forgetfulness. There is forgotten code that is killing the planet. There are forgotten servers that are killing the planet. And the scale of this is really quite large. When they try and look into it, this is a hard problem to study because forgotten servers, by definition, are forgotten. You don't know about them. That's why they're the problem. But when people do inventories, they usually find that about a quarter of their servers are running away, consuming energy, not doing anything useful. And here, I don't mean that they're serving cat pictures or something like that. They are not doing anything useful. They're not communicating to the outside world at all. And there's usually about a further quarter that are running at below 5% utilization. This is astonishingly wasteful. And so when you look at the average server, when you take into account all of those completely useless servers, the average server is running at about 12 to 18% of capacity, which is terrible when you think about how much, as Sophie mentioned, there's so much energy that goes into manufacturing that server. You want to at least use it once you've manufactured it, but we're totally failing to do that. And then, of course, there's the data problem. So around 68% of the data that is stored is never, ever used again. It is never read again. And yet, storing it consumes energy. So this is just phenomenally wasteful. And the thing is, this is costing a lot of money. But it's not just money that it's costing. It's costing a lot of electricity, but it's not just the electricity. It's also, as Sophie mentioned, manufacturing those systems consumes a lot of carbon. And manufacturing those systems, running those data centers, uses a lot of water. And at the end of the life, there's a lot of e-waste. So this is bad. But the good news is we do have solutions. So there's lots of things we can do. I'm going to run through a few of them. And the first is something that I've called LightSwitchOps. And I started talking about LightSwitchOps a few years ago, and I was the only person talking about LightSwitchOps. And now it's very gratifying. Every now and then, someone else talks about LightSwitchOps as well, which is, I think, all you can hope for your ideas. And the idea with LightSwitchOps is that when we go in and out of a room, we never feel this existential anxiety when we put our hand on the light switch and say, I could turn the light off, but what if it doesn't come back again in the same way? We know the light is going to come on. On the other hand, Every time I turn off my computer, I never know if it's going to be the same when it comes back up. Every time you turn off a server in a data center, you never know if it's actually going to be functional when it comes back up. This is something that we can fix as an industry. We need to make sure that our servers, our systems, can come back up quickly and that they're actually functional when they come back up. Because if we can do that, if we can get that resiliency and that idempotency in our systems, we can turn them off. And if we can turn them off, we can then go the next step and automate turning them off in response to demand. And we can save quite a lot by some quite simple steps. So I heard a story from Tom Coles. I don't know if any of you know him. He's another speaker. And his wife was working in the Dutch school system. And she wrote a little script that just turned off the school servers overnight. And it saved 12,000 euros. This is a huge amount of money for a little shell script. And then when you take that into an IT organization, you can get even bigger savings. So I heard a talk, and they were using AWS, and they used to leave the applications running all the time. They wrote some automation to turn them off at night, and their cloud bill went down by 30%. And if you think how big your organization's cloud bill is, that's a saving that you would take. And of course, this only works in some cases. If you have round-the-clock staff, if you're globally distributed, maybe this doesn't work. But there are still things that you can do in this area. And if you want to go further than shell scripts, we're starting to see some tooling for this. So of course you have all of the automation tooling, the Terraforms, the Ansibles, but there's some custom tooling that's being developed just for this as well. So AXA have written a cute little tool that is just for automating this shut off and turn down and scale up so people can go to the interface, and there's a web interface. It's all quite nice. And these kinds of processes, they have a bunch of benefits. Again, obviously they save the energy. They save the money. But if you can get this automation right, as you've achieved something else as well, which is you're 3/4 of the way to having disaster recovery. Because if you can shut your system down and bring it back up, then you can shut it down in the event of a problem and bring it back up. And this has, again, this sort of has some knock-on benefits. One is you've tested your disaster recovery. But the other one is all of the time, you can skate closer to the line with your provisioning. So you can under-provision your system slightly because you know you can scale it up if you need to, which is really good. So that's one thing that you can do. Another thing that you can do, which I really like, is just have faster code. And again, you know, this is something that all of us get so frustrated by slow code. Slow code is the worst. And so the idea that if we just have faster code, everything is better, is pretty appealing. And I started thinking about this, and I decided I needed to come up with a name for it. And so I came up with the name the vrrrooom model to describe this idea that basically faster code is going to save the world by saving energy. Naming is the hardest problem in computer science. I didn't think too much about the name. In hindsight, there are a whole bunch of problems with this name. The first is the SEO. Because I don't know if you can see, but there's an arbitrary number of R's and O's, the way I've spelt vrrrooom model. So every time I spell it slightly differently. And then I realized that people would go to my website and search for the vrrrooom model, and they would spell it differently again, and they wouldn't find anything. So, lesson 1, think about the SEO. But there was a second problem as well, which is I hadn't even done a simple Google search before I came up with this name. If I had, I would have realized that if you search for the vrrrooom model, Google will first of all say, you must mean the conventional spelling. Let's look at the results for the vrrrooom model. And then it shows you the model invented by Dr. Vroom. It hadn't occurred to me that there was a Dr. Vroom who had made a model. And so Dr. Vroom made a model to something to do with workplace psychology, and it's not a million miles away from what I was talking about, so it's very confusing. Naming is the hardest problem in computer science. But it gets even worse. Because if you say, no, I didn't mean Vroom model spelt the normal way. I meant Vroom model spelt the really stupid way with an arbitrary number of R's and O's. If you type that into Google, what you get is not safe for work. What you get is scantily clad women selling cars. I didn't think it through. So, but what about my Vroom model? What was I trying to say? Because it was not selling cars. I don't know if any of you saw, probably a lot of you did, this paper that sort of went round the internet a few years ago about the energy efficiency of different programming languages. I think we all loved this paper because everybody loves evidence that their programming language is the best, and other people's programming languages, like those PHP people, are doing it wrong. And so we could look at this table and we could say, I'm in a good place. Now, hands up if you're a Java person. Yeah, most of you. So I'm mostly a Java person, and so Java's number 5 in this list, and it's above Go and a bunch of those other languages that people say are, cooler than Java. So I was really happy about this. But I'm not here to talk about that. The interesting thing about this is that they measured a bunch of things. So they looked at how much time the program took to execute. They had a bunch of micro benchmarks. And they looked at how much energy was used. So those are those two columns. If you look at and they normalized it. If you look at those two columns, they're almost the same. The order is almost the same, and even the numbers are really similar. And so I plotted this to confirm my intuition. And you can see that, yeah, if you put it on a log plot, that is basically a straight line. Execution time and energy consumption are correlated. If you write faster code, assuming you don't make it go faster by doing something like using extra cores or scaling out or something like that, it will be faster. And I want to show a case study of this with some of the work that the Quarkus team has been doing, because I think it's really interesting. And historically, the way Java was designed to be run was that you would put it in a server and you would keep it running almost forever, 6 months, something like that. And so in order to have a maintainable system that you didn't stop, it had to be extremely dynamic. You had to be able to change different parts of the system while the application was running. That is not how we run our systems in 2024. We have CI, we have containers. Our applications are immutable. If you don't like your application or its operating system or any of it, you just put it in the bin and get a new one. And so now Java had this problem that it had all of this dynamism baked in that was completely and utterly pointless. And this is bad because the dynamism has a cost. And so if you look at what a Java application, a non-trivial Java application, does when it starts up, there's a little bit of stuff that happens at build time, generating the bytecode, putting it into an archive. But then there's a whole bunch of stuff that happens at runtime. So at runtime, it will look at all the config. It will do a whole bunch of loading and parsing. It will then, do a whole bunch of class path scanning. It will do annotation discovery. It will use reflection to try and discover things. And then eventually you get this sort of meta model of the world. And then eventually it will do things like starting the thread pools and the I/O. That's a lot of work before it's ready to do anything. And this is why people look at languages like Go. And the worst bit is if you start this application multiple times, which you will do because you're running in containers, all of that work gets redone every single time. This is really annoying. And it's really, it's this sort of goldfish brain runtime where it just doesn't remember the work that it's done. And that's bad. And this affects the speed quite significantly. So as an example, if you're using Hibernate, Hibernate does a whole bunch of work by reflection to try and wire in dependencies. And really, any non-trivial library will do a lot of stuff with reflection. So to figure out what JTA library you're using, it will do a class 4 name, which is expensive. And then if that doesn't work, it will do another class 4 name. And then it will do another one. And then it will do another one. And then it will do another one. And it will do that until it finds the right one. And so that means if you're using a really obscure JTA application, it has to do so much work. It will do 129 auto-wiring attempts before it gives up every single startup. And each one then ends up throwing exceptions as well. And this isn't just a JTA thing. This happens for lots of internal service bindings. And then that has an impact at startup, but then it also has a knock-on effect at runtime. So the way method dispatching in the JVM works is, because it is quite dynamic, you will have an interface, and then you have multiple possible implementations of that interface. And what the runtime will do is it will have to look at each one before settling on the one that you're actually using. And so this is called megamorphic dispatching. If you only have one implementation because you were able to get rid of all of the others at build time, then you can do monomorphic dispatching, which is nice and fast. So Quarkus really wanted to try and fix all of that waste. And so the idea that they had was, what if we initialize at build time instead? What if we still do all of that work because it has to happen, but we only do it once? And then that means that if we do repeated starts, it's efficient because it's just a tiny amount of work that's being repeated each time. So there's less waste, which is cool. And this isn't just a theoretical thing. We can see that because of this approach and various other things that the Quarkus team have done, Quarkus uses less energy. So in this chart, that red line at the bottom is Quarkus running as a JVM application. The next one above is Quarkus running as a natively compiled binary. It's quite unexpected that that takes more energy. And then above is other frameworks. The reason that native uses more energy, even though the natively compiled binary has this tiny memory footprint and starts faster than a light bulb, is because of the vrrrooom model. Because with native, you do tend to take a bit of a hit in terms of your throughput. And so that means that is reflected in your energy consumption. And so it means that native uses more energy, which is interesting. But I think what's really interesting about this is probably all of us are really accustomed to that classic computer trade-off, right? Of you can trade off your startup time and your footprint against your throughput. And what this was able to do was break that trade-off. You have better startup time, you have better memory footprint, and you have better throughput, which is really cool. And so this is a double win. Some of you may be looking and saying, well, that's very nice, but I have seen seesaws. Seesaws do not fold in half. That's not how seesaws work. This is not possible. It turns out you can get folding seesaws. So anything is possible. But there's another nice trade-off here as well, which is about human efficiency and machine efficiency. Most of us are used to the trade-off that you can choose your human efficiency, your friendly framework, or you can choose Rust. With Quarkus, what we were able to do was, again, beat that trade-off. And so it's another double win. Although at that point, I don't know if it would be like a triple win, or maybe it's square, so it's a quadruple win. In any case, it's more wins than you would expect. And the reason that we were able to do this is because moving stuff to build time meant that instead of having reflection, which is really slow, we had what's basically offline reflection. And there's a whole bunch of things that you could do with reflection that you don't do if you're writing a library, because you know it will be too slow and people will hate you. If you have offline reflection, you can do that. And so we were able to get rid of a ton of boilerplate code and really move to the model that all programming languages should have and all libraries should have, which is don't tell the computer what the computer, or rather don't make people tell the computer what the computer already knows. That's stupid. That's waste. So with logging, for example, those of you who are Java developers will know that if you're doing production code, you have to put in your logging, and the first line of your logging is to say what class is being logged. This should be obvious because that's the class that you're in. Why do I have to tell the computer what class I'm in? Because I've just copy-pasted that from another class, and it's probably wrong. If the computer worked it out, it would be right. So we were able to switch that logging declaration and say, instead, you can just do this one-line static log call. It works out the correct class. And we can do more substantial improvements as well. So if you're using Hibernate, you usually have to add in a whole bunch of boilerplate code with utility methods. And that can't really be inherited from a superclass because it depends on the exact entity that you're using. But because we were able to do this stuff at build time, we can get rid of a whole bunch of that. And so we call this developer joy. And the point here, really, is that I think, independent of Quarkus, this is what we should be going for everywhere. There's this idea of no-regret solutions, which is, let's get rid of things that we didn't even want so that we can get more of the things that we actually do want. So with Java, we got rid of the dynamism that wasn't even being used, and we were able to make things better across the board. So let's change subject a little bit, and let's talk about AI. Because was it even a conference talk in 2024 if AI wasn't discussed? These tools are incredibly useful, but sometimes they are not so useful. So for example, if you go to ChatGPT, I think they fixed this now, but if you ask what the world record was for crossing the English Channel entirely on foot, you would get a very confident answer that it was done, by this person in this day. If you're French, ChatGPT is ChatGPT, which is slightly rude and involves cats. And this is sort of funny, but all of us know that this wasn't the case. But the problems that ChatGPT and these kinds of generative models introduce can be more subtle, but also more serious, because they have a tendency to produce a lot of answer. And so a while ago, I was using it to generate some Quarkus code. And so I gave it my description, and it gave a bit of code, and then it kept going, and it gave more code, and it kept going, and it gave more code, and it kept going, and it gave more code. And I was really impressed. I was like, wow, it would have taken me ages to write all this code. But the thing is, I wouldn't have written all that code. The whole point of Quarkus is that it gets rid of this boilerplate code. And what this generation had done is carefully reintroduced all of the boilerplate code that wasn't needed. It was 70% unnecessary code. So it looked like it was saving me a bunch of work. But actually, it really wasn't, because code is not an asset. Code is a liability. And so it had introduced all of this unnecessary code. It's this illusion of efficiency. There is good news. We do have a solution. I think we can get a lot of the benefits of this kind of tooling with fewer of the downsides by just switching to smaller models. Smaller models are the way forward. They're cheaper to run, they're cheaper to train, and if you use a small model with RAG or a small model with fine-tuning, you'll probably get results that are closer to what you actually want. The other thing that you can do is you can go hybrid. We don't need to throw away all of the techniques that we have learned just because we have a new shiny tool in the toolbox. So we can use hybrid models where we have some generative AI, but then we also combine it with symbolic reasoning for some of the things that we really care about. That's cool. But these illusions of efficiency, they're everywhere. I saw on social media recently, I just heard of a founder who monitors his co-founders and employees' productivity via a Whoop group. The team is collectively averaging 5.5 hours of sleep per night. And I saw this and I thought, wow, that's terrible. That VC really needs to step in and tell his team to sort it out and get more sleep. Because if you are trying to work without sleep, it is the equivalent of working drunk. No one would encourage people to work drunk, I think. And so why are people encouraging their team to work without enough sleep? But that wasn't what it did. It went on to say, if you haven't implemented this already ahead of your productivity, already at your portfolio companies to monitor their work ethic, I strongly recommend it. And again, here we're sort of using sleep as a proxy for efficiency without realizing that they are inversely correlated. This is the illusion of efficiency. But the thing is, I mean, we keep trying to chase this efficiency, but there are limits to efficiency. Even if independent of sleep, there is a limit. One of these limits is sort of psychological, and one of them goes back to physics. How many of you have heard of Jevon's paradox? A couple of hands. So I always thought of Jevon's paradox as the highway paradox. And this is the idea that when we widen roads, we imagine that we're going to have this wide road and the same number of cars as we had before, and it's going to be bliss. What actually happens is we widen the roads and then the number of cars increase and we have the exact same traffic jams as we had before, but we just paid a bunch of money to widen the roads. So that's a psychological limit. But there are also, going back to physics, there are physics limits to efficiency. Even if you are a machine, there is a limit to how efficient you can get. And you might be surprised by how low it is. So going back to that study of engines, something like a car, it is an engine. With a combustion engine, the maximum efficiency that you could possibly get if you had the most perfect combustion engine ever is 37%. That's astonishingly low. It means 60% of the energy is being thrown out. This is a good argument for electric cars, but that's not what this talk is about. When a typical engine does not run at 37%, a typical engine runs at around 20%. And the reason for this is partly that it's really expensive to get to 37%, but it's mostly that the engine would wear out if it was run at that really high level of efficiency. And so in order to preserve the life of the engine, they deliberately detune it. And this is really important because this shows us even for machines, there is value in slack. And actually, I don't mean slack as in the human hamster wheel. I'm not convinced that there is value in slack. I have never known a product where the actual characteristic of the product and the name of the product were so completely opposed, which goes to show, just like Russ said yesterday, computer people shouldn't be allowed to name products. We just do a bad job. What I mean by the value of slack is real slack, doing nothing, having idle time. And in all systems, we see that this is really important. So if you're looking at trains, for example, trains can go faster than they actually do, but they deliberately go below their maximum speed because otherwise, anytime there was any tiny delay, the whole schedule would collapse. But by having that slack, things keep working. And you can see this in nature as well. Dogs famously have 4 legs. It is not very efficient. You could actually design something that stood up and only had 3 legs. And people did this because we like to optimize. So we designed stools that have 3 legs. This is highly efficient. But there is a problem. Because if you take your dog and you remove one of the legs in a very humane way, it is still a perfectly functional dog. It may not be happy with you for a while, but it will run around the park, it will sniff other dogs, it will do all the doggy things still. If you take a stool and remove one of the legs, that is not a functional stool. It is not running around the park sniffing other stools. It is just waste at this point. And so that resiliency lowers efficiency. We have to choose which we want. And it is exactly the same for people. If you push the system too hard, you just get burnout. It looks efficient to not be sleeping, but it's really not. I just saw this morning, which is the when I led Splunk's observability business, 90% of the SRE team resigned within 6 months due to burnout of on-call duties. So this isn't just a fluffy, let's be nice to people thing. There is business impact here. If you do not have Slack in your system, it is going to hurt you financially. And I think we've probably all been there. You know, we've probably all had the colleague, or we've probably all been the colleague that just ends up overloaded, and you go to them and you say, hey, I need you to, and they're, the answer is just like, no, I am not. How dare you ask me to do work? I cannot do work. I am too busy. And it's not good for them, and it's not really good for anybody around them either. It's just, it's a bad situation. And this is something, intuitively we probably all know this, but there's a lot of research to back it up as well. Research shows that having that time doing things that aren't strictly work is really good for business. There's a ton of papers that show this. And so what the studies tend to show is that having that little bit of downtime for employees gives you a whole bunch of benefits. They actually work harder when they are working. They're more productive, and they take less sick leave. And again, this is because sick leave is like the engine breaking down. Your employees aren't breaking down if they have a little bit less utilization. And we can quantify this pretty precisely. So if you have a positive mindset at work because you haven't just been overloaded, you will be 31% more productive than you would if you were negative, neutral, or stressed. So then the question is, okay, but how do I get a positive mindset at work? It's not as easy as just watching cat videos. The good news is it is literally as easy as watching cat videos. There was a study, they gave people a maths test, but before that, some of them, they showed a comedy video. I don't know if it involved cats, but I assume it did. And they had 12% greater productivity. So this is really good, You can go to your management and you say, I went to GOTO and I have the solution. It's cat videos. That's all we need to do. But we can generalize this as well, which is if you have that play, that leads to efficiency. I think because we work in a creative industry and play helps creativity, I think most of us can probably accept this. But there's actually another thing, which is a little bit more surprising, which is doing nothing actually also leads to greater efficiency. This is totally counterintuitive, but it is true. And there's a psychological basis for this. There's an area of the brain, or a set of connections in the brain, and they can see, using medical imaging, that when the rest of the brain is doing less, when you are knitting, when you are staring into space, this part of the brain becomes more active. What does this part of the brain do? It solves problems. It's responsible for creativity. It's also responsible for interpersonal things, interestingly. And so, again, this is something that we can prove it in medical imaging machines, but a lot of us actually know this intuitively. Because what do a lot of us do when we need to have ideas? We don't sit at our computer going, I'm going to have an idea, I'm going to have an idea. If I stare at the screen long enough, an idea will come. No, what we do is we go to the shower. And the shower is the best debugging tool there is. And there was research. This is slightly questionable research. It was sponsored by a shower company. But what this research found was that 72% of people get their best ideas in the shower. And 14% of people actually specifically go to the shower as a debugging tool. They take showers for the purpose of coming up with ideas. And so again, this is another one of those things where we can find evidence from it from a whole bunch of different domains. And so psychology and that medical imaging shows it, but math shows it as well. Because this is something that queuing theory completely confirms. Queuing theory says systems have to have spare capacity. They have to run underutilization in order to function at all. So the basics of queuing theory is that you have an arrival process. Things come in. And then you have a queue, hence the name. So the work waits in a queue, and then eventually it gets to a server process. So this could be like a person at a checkout. It could be a computer. Whatever it is, it's dealing with those incoming requests. And then at the end, the work gets done, and you have the output. This is where you want to be. But there's a whole bunch of things that can go wrong with this system, which is why we study it. So the first is that if the arrival rate's low, then you have this server capacity, and they're just doing nothing because nobody's arriving. And then we have the opposite problem as well, which is if the server capacity is too small, then you get queues building up. And so the trick is to try and find the right balance between those two. But the really interesting thing is how bad it is if you do not have enough capacity. You have to accept some idle time, because otherwise what happens, if you go from 80% utilization to 90% utilization in your system, your wait times double. That wait time is going to have a business impact. So you have to accept some idleness in order to have an acceptable SLA. But on the other hand, you don't want 90% idleness, because at that point it does start to become a problem in the other way. So you do have to take into account the cost of that idle capacity. And you want to try and find that sweet spot. But I think this is really, really good news, because what this means is that we have a business obligation. We have a technical obligation to do less work in order to improve business results. How awesome is that? And so I think we can really think of this in terms of an inverse of Jevon's paradox. Because the thing with work is that the to-do list is infinite. I used to sometimes, I'd be so behind at work and I had so much to do. And I'd think, I'll just work at the weekend and then I'll get on top of my to-do list. But it doesn't work like that, because what would happen is I would work at the weekend, I would send emails off, and then the people at the other end would reply, which was outrageous, because then it meant I wasn't actually any further ahead with my work than I had been before I sent the email, because replies came, I still had this overflowing inbox. So that doesn't mean that we shouldn't do anything, but it does mean that I think we can feel really okay about prioritizing, because we are never going to get to the bottom of the to-do list. The to-do list is infinite. We should not try and create enough capacity to deal with an infinite to-do list, because that's never going to work. Instead, we have to try and find solutions that are based on prioritization. And so again, this comes back to that trade-off, which is we think we have a trade-off between working less and being effective. But actually, at least to some extent, we don't. There's this double win where we can work less and be more effective. And the only problem really is explaining this to other people, because there is a little bit of a marketing problem with doing nothing. And if you think about like images of efficiency, a kangaroo is the most efficient land animal in the world. And this kind of makes sense intuitively, right? What do kangaroos do? They're super energetic and they bounce and they bounce. But a kangaroo is not the world's most efficient animal, actually. It's just the most efficient land animal. The most efficient animal is a jellyfish. A jellyfish does not look like a model of, what you want to tell your boss, I'm going to be like a jellyfish. Jellyfishes, they're kind of uncool and floppy, and, their whole body is basically slack. But they are incredibly efficient, so we need to try and bring in at least a little bit of that jellyfishness. And I want to close, because I am in Denmark, and so I wanted to mention Denmark's most famous export, which is Hygge. And so I was talking to a Danish colleague, and I said, I want to talk about Hygge developers. And he said, well, you can't talk about Hygge developers because that is like a total grammatical violation. You just can't say that. So I apologize for my pronunciation, and I apologize again for what I've done to the meaning of this term. But I'm taking it. And so my colleague, he said, what you have to do is you have to talk about cozy, lazy developers. So that's what we should aspire to, is this model of just having that, that nice sense of happiness and coziness and not doing too much because it's not going to be as productive as we hope. So to wrap up, don't accept waste. Waste is awful. Our world deserves better. We can sort it out. Work less, achieve more, because happiness is not waste. Happiness is not something you should be optimizing out of the system. And idleness isn't waste either. Don't optimize idleness out of the system or the system will break down. And so really what we can be trying to do is break those trade-offs. Look for that double win, because that gets us everything we want and less of what we don't want. And with that, thank you very much.